Okay. So good evening, everybody. I hope everyone's having a wonderful day. So today I'm going to be picking up from where I was last day, and then we'll be moving on to a brand new topic. Definitely. So what I'm going to be doing is I'm going to be picking up from where we talked about stacks. Now, last class I showed you a bunch of different implementations of stacks and queues. So the great part about this discussion is I showed you many different implementations of stacks and queues. And the great news is if you assume that the number of elements is no more than this capital N, this capacity. Now keep in mind this was an assumption I made for the array-based implementations. For the linked-based implementations, like our linked list-based ones, you don't have this capital N. You don't have to worry about it. But I must stress that if assuming this thing, n is less or equal to capital N, all the operations for every implementation of a stack or a queue, they all take big O of 1 or constant time in the worst case, which is wonderful, right? So you might ask why. If you take a look at each one of the algorithms, you'll see that I give you that first. The array-based one, almost every single one of them involves, I know exactly where the position of the element is, and I'd have to do some modification. So in those implementations, I have direct access. In the linked list-based implementations, all of them, I already know where I need to access the element, which will be in some note either, if we're talking about the stack, it'll always be at top, which just involves a constant number of pointer manipulations. And then for the queue, you know exactly where they are. They're either on the head of the linked list or at the tail that you need to manipulate on. Each one is a constant number of pointer manipulations, right? So in either case, you get constant time, which is wonderful. However, so having this capital N is often very helpful in practice to know this in advance if you're picking up one of the array-based implementations. However, there's a big but on this. Really big but. You can't just assume this always exists because there may be some sequence of operations that where the number of elements does exceed this constant. So I must stress that two things. So under this assumption that the space usage for all the array-based implementations, all of these are big O of capital N. And all the space usage for the linked-based ones, or the linked list-based ones, all of these are big O of lowercase n. So just be aware of this. So for example, if you have a really big array and you're not using much of it, that could be a waste of space. Now, let's consider. So what happens? So what happens when n is arbitrary? Because if I don't have this assumption in play, we have to be very careful. Now, first, the good news. Every one of our linked list-based implementations, as it has nothing to do with this assumption, their worst-case time complexities are unaffected. All linked list implementations are unaffected by this. However, our array-based ones are because this is an assumption I'm making. So just to give you a little bit of a flavor for how the array-based implementations will work, is that you have this initial capital N be what's designated as the capacity for your array. So this would be the size of the array at the beginning. Then what happens is I'm just simply going to start introducing more elements. And if the array becomes full, I need to resize the array so I can put more elements into it, right? It means I have to create a new array. I got to copy all the elements into this new array that's longer. And then I just reassign the array to be the new one and I get rid of the old one, right? We talked briefly about this last time. If you want to see an example of this, I actually do have C++ code in the notes. I think I call it expand capacity. If you take a look in the array stack implementation, I call it expand capacity. And what this will do is it's a function that just takes and copies all the elements over, and then it does it over to a certain length, where in our case, you put the new length, so how long you want the new length to be, as the parameter here. So just be aware that this is a thing, but we have to be a bit careful. So like I said, however, in the worst case, now on push or NQ, respectively, whichever one we're talking about, whether it be a stack or a queue, on push or NQ, the array may be full. So it needs to be resized. So here's the thing we're going to take into consideration. When we do this, we're going to make sure that when we make this array longer, we don't make it too long. We want to make sure it's nothing too excessive. Suppose it is resized to k times n. Sorry, k times, we'll say k times n, where this is lowercase n, for some constant, k greater than 1. So I'm just going to assume it gets resized by just some constant factor that makes it a little bit longer, enough that I can fit the next element in that I want to push in, or NQ. Now, question, if I make the array now k times n, what would be the big O in this case? So remember, when the array becomes full, so I examine to see how many elements I currently have in it. And in this case, now the number of elements is matching up with the capacity. So what I'm going to do is I'm going to expand the capacity so that it's going to end up being k times capital N, or the size, for example. At this time, they're going to be equal to each other, or at least equal at this time before I put in the new element. And when I do this operation, remember, all it does is it creates a new array of length k times n. And then what it does is it copies over each one of the elements in the old array into the new one. So how long does this take in terms of big O? And keep in mind, I have not yet talked about the actual push or NQ operation. So yeah, it's linear. Yeah, exactly. So notice that the length that I gave is some constant times n. So some constant times n. Which takes big O of n time. Then we can push or NQ as before. So you just have a little check just to make sure that if you have enough space in the array, it's a very simple check. And if it isn't going to be the case you could fit it in, then you resize the array. This will take linear time. And then you have to do you can do your push or NQ, which takes constant time. So just be aware that when you have this assumption forbidden, say you don't know how many elements there are, in the array-based implementation, the actual worst case time complexity is not big O of 1, it's actually big O of n. So that means that the summary of this is that the worst case time complexity is big O of n. And that's because this is when the array becomes full and I have to resize it. So I have a question though for you. Does this happen very often? This array resizing? With respect to, say, for example, I do a whole bunch of pushes and enqueues. Is it going to happen like every single time? Or is it going to be, yeah, it's not going to happen very often. And in fact, in practice, this is indeed the case. And also in theory, it is the case that it's not going to happen very often. So don't let this fact that it says that there's big O of n for arbitrary number of operations, where I don't have that assumption in play. It actually is just that this is something you have to bite the bullet on in the worst case, but it doesn't happen very often. So one intuitive way you can think about it is that I have a whole bunch of these cheap, inexpensive operations that happen. They all take constant time, all of them. And then every once in a while, it's going to have to resize the length of the array. But here's the thing. It's not going to happen very often. Now, the intuition behind this is you can imagine it almost like I have all these really cheap operations I get to do. And I can almost look at all these cheap operations like one that I can use to pay off the expensive one. Now, you might ask, Dan, so what does this mean for us? Believe it or not, in practice, the fact that it says big O of n for arbitrary n, it doesn't make much of a difference from a practical standpoint, because in practice, most of the time, you're going to have it where it's going to take constant time. In a course like CS340, you'll learn that this time complexity that I've just described to you is not very accurate. It's actually very pessimistic. You'll actually learn that on average, every time it's still the constant number of operations. So just be aware, even though that technically, in the arbitrary case, our push or enqueue does take linear time in this circumstance, it actually is the case that it actually is still very reasonable and practical to use. Just be aware of this nasty situation where you have to resize the array. So in practice, you would be considerate of whatever capital N would be in this scenario. So whatever the initial capacity is, if you know exactly how many elements you're going to need, just make the array that long. So you might ask, okay, so where did you get this kn from? Like, where did this come from? Is this some magical thing you just pulled out? Now, here's the neat thing. I didn't actually pull this out of anywhere that's magical. This right here is actually a practical consideration. So I'm going to say y. So y, I was about to write a question mark. I'm saying y k times n. So y resized to k times n. So in a lot of programming libraries, they refer to this k here, this k. K is called the growth factor. An array resizing is effective. So from your perspective, if I were to resize by k times n, for example, if k is 2, that means I'm going to always double the length of the array. So this growth factor that I'm using here, there's actually a special name for this growth factor when it's this. It's called a geometric growth factor. This is because it always grows up multiplicatively. So if I have it doubling every time, it doubles the length of the array if k is 2 each time. And everything I just described a moment ago about how the worst case scenario actually doesn't really happen very often in this situation. And almost all the time it's going to give you, actually on average, it's going to end up being constant time. And this is justified by something you'll see in CS340, if you take it with me. CS340, an amortized analysis. So there's something called amortized analysis, and we could use that to justify what I just stated. So if you use this growth factor idea, you could guarantee this. So question, resizing this to what? K is, and I should say in this matter. So it says an array resizing in this matter is effective. So all I'm saying is you're going to resize the array to, if it's originally n, lowercase n, which at this point it's full, you're going to resize it to be k times m, where k is some constant, where k is greater than 1. Now, just to give you an example of why I mean this is, just to be very clear, in practice, this growth factor is actually something that is a practical consideration. If you make k too big, you're going to end up wasting a lot of space. If it's very small, you may have to end up resizing several times if you know it's going to be rather long. Now, you might ask, Dan, is there some like magic number that is useful in practice? I will tell you, this is something I usually bring up in 340, but as an example, if you make k is equal to 1.5, this is actually, if you ever seen Java before, like Java the programming language, they have an array list class, which is a resizable array for all purposes. In there, they actually use k as 1.5. And in C++, I can't remember what the constant is, but there's an analogous version of this for vector class. So that one I can't remember it off the top of my head. I always remember the one for Java though. If you look at the array list class 1.5, that's the one that they used. So that was more of an engineering consideration, is that 1.5 is gonna get it so it's longer. It's longer, but it's not too long. So you're not wasting space. So this is something that if in practice if you try picking up this idea, you'd figure out what k makes sense for your application. So vector is just an array. Now, I don't want to get too specific about the vector with vectors though, but generally the idea behind it is a dynamic array, which gets resized as you insert more elements into it. So internally, you have a capacity, just like my capital N here. And if it needs to make more space internally, it can be used in resize if you want to implement your own vector, for example. You can use the idea I just described here, which is it's pretty interesting. but yeah, this idea of array resizing is used all the time in dynamic arrays. So sometimes people call them resizable arrays. So example, vector, which is another container that's in C++. See, boom, boom, boom. I talked about stacks, queues, and I also mentioned something about vectors. Isn't that cool? But yeah, no. So are there any questions about worst case time complexity for our stacks and queues? So just to reiterate, so somebody's asking why are all operations of every implementation take constant time? Now, if you take a look at all the algorithms for all of the implementations I gave you, as I said previously, if it's an array-based one, all of mine, all they do is you know exactly where you have to insert an element, so in the array-based ones, you have access to where it needs to get inserted. If you need to remove an element in the array-based implementations, all of them, you know exactly where it has to occur. So all of these are just direct access in an array, updating it, and just returning a result. In the linked list-based versions, what happens is you're either manipulating the head or the tail of a linked list. And all of those are just constant numbers of pointer manipulations and a deletion of a node, or creation of a node. Which all of those, since there's only one node being deleted or created, it takes constant time. So it's a question about, I'm just kind of confused about the difference between lowercase n and capital N. Okay, so just to reiterate from last day, this is the capacity. So it's an idea for which, say for example, I allocate an array. The array size is going to be capacity. So the length of this is going to be capital N. And the number of elements that are in my container, that's lowercase n. So for example, if I do a bunch of a bunch of push operations, this smaller amount here, so I have 4 of them, this would be like what n is, lowercase n. So capital N's purpose is the length of the array. So as you increase the number of elements in there, you may have to update the capacity capital N. But the point I'm getting at is that in practice, so just to reiterate, so somebody's asking, explain why the worst case is big O of N. It's because, remember, if the array is full, so in the array-based implementations, suppose I give you an array that looks like this. Say every element is occupying a spot in my array. What happens is the array is now full, and suppose I want to put another element in. I want to push another element into my stack. Well, I'm going to need more space in my array, but my array is full. So what I need to do is I create a new array of length k times n. Now, for our purposes, and you'll see this in the example in the notes, if you look at the array stack, I use k as 2. So I just double the length of the array. So what I do is I create a new array of double the length. Let's see, I got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So now this is double the length. So I'm going to create a new array of twice length. Then I'm going to copy all of these original elements into my new array, because I have to do it that way, because I can't just magically make the array longer. I have to allocate a new array of twice the length. I'm going to copy all of the elements that are in this into the new array. And then now I have space to put my new element in for my push. So this is why it takes big O of n time, because the array resizing is twice the number of elements, which at that time is the length of the array, which 2 times lowercase n is just big O of n. And remember, the push, all of these operations prior to that take constant time. So it's some linear number of operations plus some constant amount of operations, which is just linear. Yeah. So just keep that in mind. This is why you have to be wary of this assumption that I've made here, is that in general, you can't make this assumption. In practice, you can, because you'll know more information. But for functional purposes, for an arbitrary case, this would just be some number. It's just whatever the initial length of the array is. And we can always update this capacity in the future when we resize the whole thing. But yeah, no. So the good news is that we can implement efficiently stacks and queues, and there exists many ways to implement them. So that's good news. That's the good news. So are there any other questions about the time complexities for our stacks and queues? So the good news is that in most practical settings, you can have nice, very efficient stacks and queues. That'll take essentially constant time all the time in the worst case. And keep in mind that's for all the operations. That includes, so if we're talking about the stack, it's push, pop, peek, size, is empty, all of them. Just like for the queue, we have enqueue, dequeue, we have front, we got is empty, and we got size, right? All of them I could do a big O of 1, which is a wonderful thing to have. So anyways, if we're okay with this, I'm going to proceed to just make a couple quick remarks before I get to our next topic here. So it's great because I got to talk about a few extra things that I wasn't anticipating of chatting about here that I could kind of touch upon. So I must stress that there exist many different kinds of containers. So I'm just going to refer to this little side talk about, I'm going to call it Containers Ahoy, because it makes it fun. So there exist many kinds of containers. There are many kinds of containers. So we've seen what a stack is, right? We've seen a stack. We've seen a queue. Another one is called a list. So these could be unsorted or sorted. And we also acknowledged actually another one just a moment ago. It's called a vector. So these are dynamic or resizable arrays. So you might ask, okay, so what's a list? Here's the great thing. You're going to see these in the lab, actually. So you're going to get, there is a lab that's dedicated to talking about lists. So you'll get to see these during lab. So just be aware that there's these other containers that exist, and all of these have, all of them are in STL. So if you ever wanted to, in practice, so I'm going to say all of these in C++ have implementations in the standard template library, or you may know it as STL. Now, one thing I wanted to point out for you, just because I have to put it somewhere in our discussions here. So it's a question, what is it after containers in the title? An exclamation mark. It's containers ahoy. You see, it's just an exclamation mark. So one thing I wanted to point out is that like with stacks and queues, you can have many different implementations for any one of these containers. So we talked about a variety of ones for stacks and queues. Lists and vectors, technically speaking, can also have different implementations. I wanted to mention just an example for us. I'm not going to go into too much detail here for our discussion, but I feel like I want to mention it for us. So just as an example, and suppose I wanted to have a list. Now, in a list, you normally want to have the ability to index into a given spot. You normally want to be able to access the beginning or end, or iterate through all of the collection using something called an iterator. I'm not sure if you've talked at all about iterators in a previous class. Let me know, by the way, if you've seen heard of a thing called an iterator before. If not, you will get exposed to this at some point. Okay, I'll definitely make sure to touch upon it at some point. So, for example, if I have a list, one way you can implement a list is using something called a doubly linked list. Now, here's the neat part. You know what a linked list is, right? You know what one of those is. You might ask, yes, it's for if you want to go through an entire collection, you can actually set up a really nice generic structure that goes through every element in the container or a collection. So keep in mind, these are just some containers. Exist many others. You can define something called an iterator that goes through each one, and it's as simple to use as just using something like a loop. It's really a nice structure to use for our collections or containers. So let's talk briefly about a list. So I just mentioned briefly what the purpose of a list is. It's quite similar to when we talked about an array, except it just has some specific features to it. You're going to see these in the lab, for example, when you get to play around with this a little bit. I wanted to mention that there do exist ways to implement a list. One way is the so-called doubly linked list. And you know what a linked list is, but I need to expose you to this at some point. So I wanted to show you this just so that you could see what it's about. So you might be familiar with a linked list, right? We have it where we have a next attribute. Now, what I'm going to do is I'm going to do something that's a little bit different here. Notice that now I'm going to have some pointer to something else here. Some people call this the trailer. I'll call it the tail just to keep it simple. And then we have the head. This doesn't look too much different, right? So I have the data. I have next. But I have another attribute as well. It's called previous or prev. And it's really simple. It's just a pointer to the previous node. So the tail itself is going to point at every node that is, so it's going to point at the last node in the list. And each one of these is going to point at its previous node in the linked list. And the neat thing about this is that when you go through each one, when you get to the end, it kind of loops back to itself if you follow the pointers. But the advantage of using a doubly linked list as opposed to a singly linked list is notice that if I start at the tail back there, I don't have to know anything else about the front here. I don't have to follow through the front to get to the back. I can start at the back or the tail of the linked list and work my way to the front if I wanted to, which is often helpful if I need to iterate from the back. Like I need to start at the back and I want to explore from the back, or I want to insert at the back, I want to remove from the back, or if I want to insert from the front, I want to remove from the front. You could do it this way as well. But the point is that I wanted to show you just to see this idea of a doubly linked list. So it's really just the exact same idea you're familiar with, just we add in this attribute called prev, which is just going to be a pointer to the previous node in the linked list. And at the fronts and the backs, it just means it cycles back to itself. But yeah, no, I just want to bring this up. So there exists many ways you can implement all sorts of containers. This is just an example for you. So you'll see, for example, during the lab, when you see lists, you might get to play a little bit around with the STL for a list, if my memory serves me correctly. But yeah, that's all I have to really say about stacks and queues. It's okay if we move on to our next topic. So I just want to touch just lightly on this. I'm not expecting you to be a pro at doubly linked list or anything. I just wanted to expose you to the idea. Yeah, that's exactly it. It just points at the previous node. That's all this is. So now that's the only thing that's different now. And the neat advantage of this is that now, if you ever find yourself at the end of one of these, it just cycles back to itself. So if you go prev on the first node in the linked list, it just comes back to itself because it's pointing right at head, which is pointing at the first node. But yeah, it's not that much different. It just has the advantage of being able to navigate from the front or the back, the front or the back, or the head or the tail. And this allows you to have access at the front or the back, or tail. And this gives you a little bit more flexibility to play around with. So in some containers such as lists, these become rather helpful. So anyways, if we're okay with proceeding, I want to talk about our next topic, okay? Our next topic is sorting. Yes, we're finally talking about sorting. So let's head over here, okay? So we're going to talk about sorting. Now, the great thing is that you've already talked about sorting a bit. So I'm going to first kind of prime us for a discussion about sorting. Kind of remind you of some of the sorting algorithms you've seen before. And I'm going to use that actually as a leverage point to start talking about some other sorting algorithms, just to kind of expose you to how or where these ideas for sorting algorithms come from. So there's several different ways to derive these algorithms, but I'm going to show you some ideas, and I'm hoping I might expose you to some ideas you haven't thought about yet about sorting. So I must stress that the sorting algorithms we're going to consider here involve so-called comparable elements. So that means, just like what I think I talked about this previously, if not, one very simple way you could think of this is I want to be able to, so if I have some set of elements I want to sort, I have to have some way to compare one element against another and tell me if one element comes before another element or the element comes after my element. So we have all sorts of different data types that are capable of this. So I'm going to say we are considering the sorting problem where we are given n comparable objects. So I must stress many types are comparable. So just as an example, you know if integers, for example, these are comparable. Numbers typically are comparable. Strings are comparable. Characters can be comparable. Effectively, as long as you can define some function that can tell you that one element comes before another element and it works for every pair of elements in your collection, you can say that they're comparable. Usually in a programming language, you'll find that there'll be a function. So often, you can define, I'll say comparable in quotation marks, via, now I'm just giving it this name. It doesn't have to have this name, but you'll find a lot of programming languages they'll call it compare or compare to, via a compare to function. So what does this do? It will return a value, and it'll tell you how close you are to that value. If it's 0, for example, that means it has equal precedence, or it is the same as the other element. Now, it doesn't have to literally be the same. It's just when I list the elements, it is of equal listing value or precedence. And different compare to functions operate a little bit differently, but the idea is that usually these functions return like -1 or 1. -1 means comes before. 1 means usually comes after. And you could do this with numbers, right? Like you could conceivably make a function that tells you, you could compare if one number comes before another or if they're of equal value, for example. So you can also say 0 means same. So if I wanted to compare two numbers, could anybody give me an idea what one of these compare to functions might look like? Keep in mind you can have inputs it might take in, or if it's say an object, you can always have it have a compare to method or a member function that's within it. And in fact, you'll find that many of the data structures you're familiar with, such as strings, will have such a function. Anybody have any ideas of how I would go about this with a number? Think of the most obvious thing possible. So suppose I give you two numbers, x and y. So suppose that you can even make these the parameters for this function, for example. And I want to know if x comes before y or y comes before x, or if x is equal to y. And I want it to make it so it returns these values. Now keep in mind, I'm just looking for the idea. Yeah, exactly. You just do a comparison. You just check if x is greater than y, or you check if x is less than y, and then you just return the value for each one of them. It's just using if-else statements, exactly. So really this idea isn't that strange, right? You know how to do this with integers, right? We talk about numbers. What you just described in the chat is exactly what I'm thinking about. And you could define these compare or compare to functions for any data types that you're interested in. So keep in mind, you can always define your own comparable objects. So one assumption I'm going to make in this section is that I can compare objects. So if I want to use this compare to function, I'm going to assume I'm going to use an abbreviated version of these, such as using like less than or greater than, or less than or equal or greater than or equal to talk about them. When I actually mean compare to, and it's usually these numbers. If I need to do something more specific. If we're dealing with numbers, it's really easy. And yes, you could use a template function. Very good. You could do that as well. Very good. See, everybody seems to be on base here today. I really like that. So one thing I want to point out is that it doesn't just have to be numbers or integers or strings or characters. You could define your own comparable objects. So these sorting algorithms are very general. The assumption I'm going to make is that this compare to, this is going to take, it takes big O of 1 time. That's the assumption I'm going to make underneath all of this. And it's very natural when we're dealing with numbers. So you're going to find that I'm going to play around with numbers in this section. So everything I'm going to say remains true as long as compare to, or whatever I'm using for comparing my elements, takes constant time. And in our model of computation, comparing things like numbers and whatnot all take constant time for comparison. So is everybody okay with this so far? So I just wanted to give us a flavor for how general these sorting algorithms are. And all the sorting algorithms you've probably seen up to this point fall into this category. And you may know of these. The sorting algorithms that you may have seen are called comparison-based sorting algorithms. So you may have seen comparison-based sorting algorithms. So these are sorting algorithms that are based on the idea that I can compare two elements. So if I want to know if X comes before Y, that is a question, a comparison. So why does it have to take constant time? It's because I'm assuming in my model when I deal with numbers or characters, not necessarily strings, but it depends on the measurement for the strings, characters and numbers, that when I do comparisons like less than or greater than and so on, all of these take constant time. It makes the calculations a little bit easier to play around with, and typically when you compare two objects, it typically does take constant time. But I must stress that there are going to be weird exotic cases where you define a data type where you have to evaluate whether it comes before or after by evaluating more than just, say, two numbers or something like that. Which it rarely happens, but it does happen. That's why. So this is just an assumption I'm making. But keep in mind that this is an assumption you'll run into almost all the time. So for example, if you have objects that, say for example, have an ID in them that is a number, and say you want to compare between two different objects with different IDs, like say this is some idea, so each of these objects has an ID and say it stores a bunch of data. If you want to know what order they need to go into, suppose that you're sorting by the IDs from smallest to largest. One of these functions to do the comparison would just be checking if one ID is less than the other ID. It's no different than what we just said a moment ago about these two integers. It's wrapped up in the concept of a class and an object. Yeah, and you can overload this as well. So if you ever want to redefine how you compare objects, you can most certainly overload as well. Very good. So this brings me to talking about basic sorting algorithms. So there's going to be algorithms I'm going to assume you've seen before. So we're going to talk about, let's talk about basic sorting algorithms first. So I'm going to say you may have seen some sorting algorithms. That S is looking a little funky. Some sorting algorithms before. So I'm thinking about 3 different sorting algorithms off the top of my head. So there's 3 that I imagine you probably have seen before. So can anybody tell me some sorting algorithms that you may have seen before, say in 115? Yeah, selection sort is one of them. Ah, yes. Yeah, so those are the 3 I was looking for. Perfect. So we have it's selection sort, we have insertion sort, and there's also bubble sort. So these are all algorithms that solve the sorting problem. So these are all algorithms, they all solve our sorting problem, all of them. Now, you might say, okay, Dan, what do you want to talk about with sorting then? So first thing I want to point out, all of these in the worst case have quadratic running times, right? So all of these take worst case big O n squared time. All of them. All of them take worst case big O of n squared time. And all of them are based really on one fundamental idea. So the first thing I want to point out is that all of these are fundamentally based on one similar idea. Now, that doesn't mean that they're all going to be the exact same, but they all are based around one kind of key idea. They all do it a little bit differently, though. And there's different ways you could derive this idea from this. Very often, with these algorithms, all of them are based on one idea. It's very simple, is that I have one element. I want to know if this one, with respect to another element, is it partially sorted? So, for example, if I'm considering something like bubble sort, well, notice that I have a lineup of my lovely friends here. You'll notice that my friend here is taller than my friend to my right. So one way I can improve how sorted the array is, I can always swap these two, right? So you would keep repeating this process along from left to right until the whole array becomes sorted, right? You'll do this once, then you'll do it again, then you'll do it again, then you'll do it again, all the way through. That's effectively bubble sort, right? Now, there's other ways that you can take the same idea. For example, in insertion sort, I go from left to right, and I simply look at each one and I say, hey, look, am I sorted with respect to myself and all my friends to my left? And I perform a shuffling process by swapping the elements until I find a spot where my element fits. So for example, I look at my friends so far this is okay. However, when I examine my friend here, I notice I need to swap my friend, I need to shuffle this friend over so I can fit in there. And now all of this is partially sorted. But notice the key idea here. Every single time I sort with respect to the element that I'm looking at, and I swap with my elements that may be beside me or in another spot in the array. It's always about me and what I'm doing with respect to another element. I'm comparing the two. Now, the idea of this is that I'm going to be looking over the entire thing as opposed to, generally I'm looking at pairs of elements, right? So if I were to keep going through this process, you could see that I would just simply now consider this one. Okay, so this is sorted with all of these. This is now technically I'm going to count this arm as making this friend a little bit taller. So I'm cheating a little bit. I think technically my cowboy friend is a little bit taller, but arms up means it's like cheating. So when you talk to your friends about who's taller, just put your arms up. But you'll notice that if I do this for each one of my friends now, notice everything, I don't have to do any more swaps. But all of these are based around a very similar idea that's like this. Now, all of these are examples of things called in-place sorting algorithms. So I want to talk briefly about that before I get too ahead of myself. So let's head over here, because I want to talk about different features sorting algorithms have, because these are things you have to consider in practice, but also these are features of different sorting algorithms. So I just want to define what in-place algorithm means. It's a little squeaky. In-place algorithm. So an in-place algorithm uses a small, constant amount of extra space a trait discussed for sorting algorithms as the input is transformed by the algorithm for the output. So in plain language, just what this means is that if you actually count up the amount of extra space your algorithm uses, it's always going to be constant. So you have your input array, and then you have every bit of space your algorithm is going to use. So what in place means is that when you count up all of the memory your algorithm is going to need, it's going to be big O of 1 in addition to the input. So one thing I want to point out is all three of the algorithms listed over there are in place sorting algorithms. All they do is swap around elements in the array. They don't require you to create a brand new array or anything like that. So if, for example, your algorithm requires to build a new array, you know right away that that algorithm is not in place. Because it's going to require, in that case, if the array is of length n, if I create a new array of length n, that's going to require big O of n additional space or extra space. So I'll say all three algorithms mentioned are in place. Now, one thing I really want to point out for you is that in the game of sorting, you have to be considerate of how many elements there are to sort. Now, for a general sorting problem, we can always be given some array of some length, but that could be any array of any one fixed length, right? But in practice, sometimes some sorting algorithms are better or more appropriate to use over other sorting algorithms, at least from a practical standpoint. People have been studying sorting since at least the late 50s. So just keep in mind that people have been looking at these things for quite a long time, whether it be practical settings like implementing sorting algorithms for libraries, or just simply the study of them in themselves. So just to be clear, that means that, I'll use big O of 1 extra space. So this will just simply be your temporary variables for storing your swap. So whenever you make a swap between two elements, you just need a temporary variable, or you have your counter variables. All of those take a constant amount of space. This is in contrast to building an entire array of length n, for example. That will allocate, and it requires much more than a constant amount of space. So, other thing I want to point out. So, as I mentioned, all of these rely on swapping, but in particular, it's always about improving with respect to whatever you're swapping, the number of elements that have been sorted. So, for example, when I talked about insertion sort, it scans from left to right, but every time I perform the successive shuffles to put them into the appropriate spot, I can tell you at that point, and everything to the left of it is partially sorted. This is a natural invariant for proving the correctness of something like insertion sort. So all of them have features that are just like this for proving their correctness. So one thing I want to point out as well is that the quadratic time I gave over there, that's also true in the average case. So one thing I should also mention, that these are all big O of n squared in the average case as well. I was going to mention it over there, but I got kind of excited about talking about this. So just keep in mind that there isn't some magical case where it's just going to suddenly do amazing, except for very specific types of input. So for example, if the array is very closely sorted, some of these algorithms will examine the array from left to right, kind of like, for example, insertion sort, for example. It just scans through, sweeping from left to right, and if it's really close to being sorted, it just kind of does a couple shuffles, then it moves along, and it keeps going along. So in those cases, insertion sort is a very nice choice for a sorting algorithm when the number of elements is not too massive, but it's most certainly one of the better sorting algorithms of the three. So one thing I want to point out for you. So all these sorting algorithms, are effective for small data sets. And I must stress that this is true even when I talk about the more efficient algorithms I'm going to present to you shortly. So you'll find very often that if you ever dig up any of these library source code, very often you'll have one of these spiffier sorting algorithms, one of the ones I'm going to show you, for example. And then what happens is when the problem gets small enough, it applies one of the three algorithms that I have over there, because they tend to be rather effective when you have a very small size for them. So just be aware that that is something of a practical consideration, but right now we're going to look at the worst case time complexity and the average case time complexity overall. So I just feel like I need to mention this. So are there any questions up to this point? Because I'm going to start talking about some algorithms. We'll talk about one here today, and we'll probably finish up talking about it next time. What is the average case 2 there? So this is 2. It just says 2. So I'm just saying that all three of these algorithms have big O of n squared for the average case. That's all I'm saying. What about big data sets? Now notice that the running time is quadratic. So as the input gets bigger, it's going to scale quadratically. Now I'm going to tell you up front that we have actually faster algorithms, asymptotically speaking, from our complexity standpoint, that will be able to achieve better running times. And I'm going to be showing you 2 such algorithms. So when you have smaller inputs, these algorithms have some advantages. For example, like I said earlier, what they do is they go through my friends like this. And if the array has a very nice structure to it, such as it's really close to being sorted, or for example, it's already sorted, it has a very easy to predict behavior for which it's going to operate. Unlike what happens with some of these more sophisticated sorting algorithms I'm going to show you, which in the average case, they even do cause some kerfluffles, and they sometimes have some complexities to them, where in practical situations, these much simpler algorithms in practice tend to work quite well. So the extra space is mostly used for making the swap function easy. Yeah, so if you're wondering what this is all your temporary local variables for your function. So these are, for example, the temporary variable you use for swapping your elements temporarily. This is used for your counter variables in your function. That's what big O of 1 is. It's just all of your local variables. All of those take up some constant amount of space. They don't grow with independence of n. This is in contrast to allocating a new array of length n. That will not be big O of 1, it'll be big O of n. Very good question. So anyways, when we talk about our first algorithm of the 2 I want to highlight for you, the first one is actually what I would consider the workhorse of the sorting world. So I thought I would start off with it first. So many sorting libraries will use this sorting algorithm. So it is both a practical and theoretic interest. And there's many things about this algorithm I could easily study and spend a solid week with you on it. But because of the nature of this course, we're going to probably spend a lecture to a lecture and a half on this specific topic. So we're going to be talking about Quicksort. So let's talk about Quicksort. Now, one thing I want to bring up is that unlike these other algorithms, the next 2 algorithms I'm going to show you are recursive. So these other ones are really natural to describe, and they're very easy to describe with nested loops, right? These ones are the next 2 algorithms I'm going to give you are very natural to describe using recursion. Sorry, I'm getting very excited at the moment. So first we're going to explore Quicksort. So I want to kind of walk you through kind of the justification, or like the underlying idea that makes Quicksort different from the other algorithms we talked about. So you remember when I talked about all 3 of those algorithms, all of them are based on some very simple idea where I take each one of these and I compare it with, say, my neighbor, the one right beside me, the adjacent element. And I lost my dog friend. Here we go. Each one of them I compare one element against another element, right? So I'll compare this one against this one, and then I perform a swap. Or, for example, I shuffle over elements, and I make comparisons and I swap them like that. The idea we're going to use that's a little bit different is it's a little bit thinking outside the box compared to this. So instead of comparing a pair of elements like this, what I'm going to do is I'm going to give an idea that's it's very outside the box kind of thinking. So I'm going to think about sorting, but I'm going to think about it from a recursive manner. So here's the idea that I'm going to present you. Now, first, before anything, I'm going to make sure that I'm going to move these around a little bit. Oh no, I think this friend is actually technically taller than my green friend. I think so. So anyways, imagine I'm given my friends here, and they're listed, the measurement for which I'm comparing them is by their height. And like I said, putting your arms up, it doesn't count as cheating, okay? So here's an idea. Suppose I pick some element in my array. Say this one. Now, in the previous algorithms, I would normally compare this against one of those other elements, and I would perform some operation like a swap, right? Now, here's what we're going to do that's a little bit different and outside the box. So what I'm going to do is I'm going to consider my element against all the other elements. But I'm going to do it in a very specific way. So what I'm going to do is I'm going to take all of my friends that are shorter than my friend. I'm going to put them all one side of my friends over here. And then I'm going to pick all my friends that are taller than my friend right here, my cowboy friend. I'm going to put them all right here. Now, I'm just going to take them in the order I have them here. So, for example, I have my green friend here. I got my blue friend here. Well, my turtle friend goes over here, right? So now, what I have here actually are, you can think of it as, I have two groups here. I've got all my friends that are at least as tall as me, and I have all my other friends that are taller than me. So now I have three groups here. Now, thinking recursively about this, imagine I look at this group. What I could do is I could pick off one of my friends. Suppose I picked, I don't know, say this friend. Say my other green friend. What I can do is I can group my friends in this subgroup by those that are at least as tall as me or those that are taller. So for example, my friend here, just because of their hat, they really like to feel a little taller, so they wear the hat. Is taller than this friend. Versus over here, I could do the same idea, right? I could have where I group it around one friend, say this friend here. There's going to be some of my friends that are at least as tall as me, and then there's ones that are taller than me. So what I could do is I can look at each one of these groups, and now I can look at each one. So notice that I have one friend here, one friend here. I don't have any more friends to compare here. And I have no more friends to compare here. So there's nothing else I need to rearrange. But now notice what happens. It's all sorted. So here's the idea. Instead of thinking about my element and comparing against one other element, think about my element against all the other elements, and I'm going to group them into two buckets. The ones that are at least as big as mine. Sorry, the ones that are at most me in terms of the measurement, and then those that are indeed larger than mine. So we're going to give this group a name. I'm going to call that L, and I'm going to call this group G for the less than group and the greater than group. So this is actually the heart of what Quicksort does. So first, does everybody find this idea a little bit, it's a little different, right? But it most certainly has at its heart something that seems very recursive to it, right? So instead of this is a very simple way I could think of it. The previous algorithms are all about, hey, look, I compare it against one of my friends, I do something. This algorithm is very self-centered. Everything is about one person, and then I compare them against everybody. So it's a very selfish algorithm in that sense. It's not greedy, but it's rather selfish. It compares it against every other one. So, as I lose my marker, it makes things fun. So, let's talk about this. So here's the idea. So imagine I have my array, and I'm going to designate an element. So I'm going to designate an element called the pivot. It's called the pivot. In my picture, I'm going to call it X, but it doesn't have to be called that. It's just the name I'm giving it in this picture. So imagine I have my array, and suppose I have it right here. Now this is just a picture. Just be aware that the pivot could be in other spots in the array. Now, what I would like to happen is I'm going to split around pivot X. And I'm going to split these into two groups, like I did just a moment ago. So I'm going to split it into one group where all of the elements are less than or equal to X. And I'm going to have this other group that consists of all the elements in the array that are bigger than X. So each of these I'm going to sort recursively. So each one of these I'm going to sort recursively. Then, when I'm done sorting each one of these, what I'm going to do is I'm going to take this, this, and this. I'm going to put these all together. Just like I did with my friends right here. So I'm going to designate an element, the pivot, and then my job is to arrange the elements so that all the elements that are at less than or equal to X, I'm going to put all of those on one side of the array, kind of like my picture. It doesn't have to look like this. And then I'm going to have all the other elements. They're all going to be greater than X. They're all going to be on the right side. I like the intuition. Somebody pointed out that's kind of like binary search. I like that intuition. I'm going to bring up something about that probably next class when we get to it. But I want to kind of walk us through kind of just the idea here. Now, Quicksort is an example of an algorithm that uses a technique called divide and conquer. So it uses an algorithm design technique called divide and conquer. So what does that mean? We divide the problem. We divide the problem into subproblems. Recursively. Solve each. Then conquer. Now conquer, I'm going to put in quotation marks because this always depends on the algorithm. Then conquer the problem instance. By putting together all these sub-solutions. So these are all the solutions to these sub-problems. Put together all these sub-solutions to solve the problem. So that's what divide and conquer is. So divide and conquer is an algorithm design technique. It's a much broader family of types of problems, different algorithms that you can use to solve problems. Quicksort is a classic example of one of these. So I'm going to, just for the purposes of time, because I think it's probably the best place I stop right here. When I come back next time, I'm going to talk about what Quicksort is. We're going to do an example, and then we're going to talk about its analysis, okay? So when we come back, we'll do that, and then we'll talk about our other sorting algorithm called merge sort. So next class, we'll be talking all about sorting, okay? So I'll stop right here. I want to say thank you very much, and have yourself a beautiful day. I'll see you later.